Thank you very much, Shuwen. Well, at least I will try to talk at something somewhat related to that. We'll see how it works out. Tend to go off on tangents. I would like to thank the organizers for putting together this conference, and in particular, thank Steve Zadich, who cannot be here, for a lot of inspiration. Many of things related to this work and many other things, and the general theme of the conference. So I talk about Feynman propagators, which have already come up quite a bit, mostly in the QFT related for QFT related reasons. But so I think I give as a focus, I will talk about things that are somewhat maybe transversal to the QFT purposes, which is so questions like actual inverses. So that is to say, honest inverses of operators on function spaces. So is there are there unique inverses in some settings? I mean, not because of symmetry, but because of the overall structure of the problem. Somewhat related thing. I mean, usually one, for whatever historic reasons, one likes to think about Cauchy problems and causal inverses, but other inverses might very well exist on reasonable function spaces. Another reason why one might want to do these sort of things is because pseudo-Riemannian metrics of general signature, which came up in Diana's talk, for example, last week, in the split signature thing, they have sort of a bad rep. And that's not really the fault of the poor pseudo-Riemannian metric. It's the fault of trying to do Cauchy problems. So, so how about general pseudo-Riemannian? Metrics of various other signatures. So can you do inverses of D'Alembertians of whatever you want to call these wave operators in these settings? And then maybe I will mention a somewhat funny or strange, depending on how you want to think about it, strange Riemannian similar examples. I mean, in a way, it's not really strange that it's Riemannian. The expectations for Riemannian and elliptic problems going in certain ways come from local theory. And inverses are global. I mean, except for if you get amazingly lucky, the chances of which are zero, unless you are in a very constrained universe, in which case it might be that you almost everywhere get local things, like if you work on wave equations exactly. And you look at the causal propagators. So inverses are, in general, global. And so for non-compact Riemannian manifolds, I mean, it's not really the Riemannian manifold, it's the Laplacians, say, geometric operators associated with this. So these things can behave like pseudo-Riemannian ones. And that's really what, say, Euclidean scattering theory is about. And so, of course, this perspective on scattering theory goes back a while in various settings. But I think in somehow this kind of form was really emphasized by Merrows in his geometric scattering theory approach. Okay, so that's the sort of things I want to mention. So it takes a while to describe various settings. So the easiest thing is I just give one concrete case, and then at least for the first two, and then maybe say something about the third. And then we just keep using the word Minkowski or whatever signature analog of this, rather than working in sort of general class. So, so the one difference between elliptic, I mean elliptic maybe in a slightly generalized sense. So parabolic is often acting like elliptic, and non-elliptic problems is, well, I mean, not terribly degenerate. So once you get terribly degenerate, of course, things go really wrong. So not too degenerate, so not degenerate. Elliptic problems is propagation phenomena. So in the elliptic problems, I mean, apart from that, if you think about what happens, outside compact sets, like in this case, nothing happens, so nothing moves, right? So depending on your perspective, it's good or bad. Like if you want life to be simple, like an analyst, and you care about having a relatively simple solution to your problems, it's good. If you want excitement, it's not necessarily so good. So the difference is propagation phenomena. And so correspondingly, this has already come up, of course, in a number of times. The relevant thing will be on the cotangent space. M is the underlying manifold, and then you have this cotangent space, say minus the zero section. And so in the manifold you had your metric, whatever signature, and then on the phase space, on the cotangent bundle, you will have its Hamilton vector field, given by the symplectic form. And you really care about this inside the characteristic set, or the energy shell. So inside, let's call it sigma, which is where G is equal to 0. So G is, actually, let me just write it like this. I'm going to call it big G. So big G being the geometric function. So right, this is the, quote, squared length covectors. Okay, so this is the, you have this Hamilton vector field, and then by characteristics, if you are like Hermander, or not by characteristics if you want to emphasize. So by characteristics are just the integral curves of this HG. I mean, maybe you want with the factor of half in or something inside the characteristic set. And so the basic phenomenon is that energy propagates in phase space, so in T star M, along this HG integral curve, so along the bicharacteristics. So, right, so the number one thing is that here, of course, that this is, you really care about them only inside sigma equals 0. So depending on attitude, maybe they shouldn't even be defined outside. I mean, G equals 0, maybe they shouldn't even be defined outside sigma. In any case, if you now take the corresponding wave operator, or, so this is the D'Alembert, whatever signature, maybe it's Laplacian. So if you take this corresponding D'Alembert, this is, of course, elliptic outside sigma. So in most of phase space, like sigma is, codimension 1, it's measure 0. If measure theory ruled the world, this would be irrelevant. So it shows that measure theory doesn't rule the world. Anyway, so it's elliptic outside sigma. And so in particular, you have elliptic estimates. estimates hold sort of microlocally. So this is the sort of thing that you can estimate. So elliptic estimates look like this. So say in Sobolev spaces, so say the sort of local version, local theory version. So I'm not talking about infinity, etc., just so I have a down-to-earth statement. So typical estimates look like you can estimate U microlocally, so B, U. So this is a microlocalizer. In other words, localize to a conic subset of this T star M minus the zero section. Really, again, this is one of those things that people like simple things like the cotangent bundle as opposed to quotients of it. So really, subsets of the quotients. So this is the cosphere bundle, which now has no dependence whatsoever on the metric. So anyway, the estimates look like this BU in some Sobolev space, say HS. This is so say the operator is second order. Okay, so it's fixed now. So it's going to be estimated by a constant times let's call it B1U. Let's call this B3U for the sake of it. Box U, and then S minus 2. And so this is what elliptic estimates look like. And so what you need here, that B1 is localizing to, let's put it this way, a compact subset of this S star M minus, I'm just going to call it sigma also in this quotient. So if you localize there, and B3 is, and so this is order 0, it's going to be a pseudo-differential operator of order 0, so you should think of it as a cutoff in phase space. And B3 is elliptic. So it's also localizing, but it's elliptic, so it's like non-degenerate on the wavefront set, so where this is non-trivial. And so the picture is, here's my cosphere bundle, my underlying manifold. These are the fibers, so you have a S star M, I have some subset here. Maybe my B1 lives here, so the wavefront set of B1, and my B3 should be elliptic. Right, and then so this is what for a second order operator an elliptic estimate looks like, and the wave operator is almost everywhere elliptic. Okay, but measure theory doesn't answer all our problems, so this is not sufficient. Of course, very exciting things happening, and so the propagation phenomenon is what happens in sigma. And so again, the local theory. And so here, this quotient already shows that one has to pay attention to something. So the Hamilton vector field integral curves were defined in here. I'm taking this quotient, and so what might happen is that they reduce to, the curves themselves reduce to a single point under the quotient. So pre-quotient, they are an orbit of R plus. And so locally, if Hg, so in this case, it's automatically the case, but if I had some more general thing, it's not, is not radial, but this will come up in other settings soon, in not a multiple of the dilation vector field, which is automatic here. But I want to emphasize this because this is important for later things. So in sigma, energy, which is saying estimates, propagate. So this is really, the energy estimate, the standard energy estimate done in phase space, where you already dealt with the almost everywhere statement, which is the elliptic estimate. Propagate along Hg orbit integral curves. So what does this look like? So this looks like you can estimate U somewhere again, let's do it in HS, by u somewhere else, HS, and then plus, of course, need to use the equation. So of course I left out my error term, because I got carried away with the explanation. So of course there's an error term here, so which is relatively compact error term. So it's a very weak error term. So this is, I mean, in this case I'm emphasizing local theory. So it's a like locally, let's put it this way, since I'm doing local theory. So quote trivial, unquote. I mean, trivial doesn't mean zero, but it's trivial for analysis. And so the same story here. So, but the difference is that there's a shift of one order here. So rather than s minus 2, this is the so real principal type estimate. You lose one order, and again you have this sort of quote trivial, unquote error. So this is anything. And here the geometry is, I have my beautiful bicharacteristics. This is the AG integral curves. And I want to estimate u here. And what I need is that whenever I take, say I want to propagate estimates forward along the flow, then what I need is whenever I take a point here, I go backwards from it, then I should be able to control things. So I should have a control set. So this is going to be elliptic set of B2. So that whenever I take a point here, flow backwards, I will get back to this set in a fixed amount of time, finite time. I mean, by time I mean flow parameter. And I should be able to do this while the equation holds, so remaining in the elliptic set of B3. So that's the so the microlocal version of energy estimates. And so, so that's the difference between the Riemannian and the pseudo-Riemannian case. Because in the Riemannian case, of course, sigma is empty, so you never have to worry about these things. In the pseudo-Riemannian case, it's non-empty, and so you have to start worrying about this. And so, but so correspondingly, you need to know some in order to have an inverse or even a Fredholm theory. You need to worry about propagating estimates. And so for that, you need to worry about the structure of the integral curve, so the bicharacteristic flow. And one more thing that you need to worry about is that, so this estimate is beautiful, right? Because the elliptic estimate, because, okay, I put in some microlocalizers, but let's ignore them for a moment. They have the structure that u somewhere, I mean, so that u period, because I'm ignoring the microlocalizer, is controlled by the operator applied to u, modulo trivial error. So that, together with the adjoint version and dual spaces, is what you need for Fredholm theory. So this doesn't look like that, but because only one reason, the one reason is this pesky B2 term. So you have to have control somewhere else. So what you really need in the non-elliptic settings need to be able to start propagation estimate somewhere. Okay, and so for wave equations, going back to well before Cauchy, the standard thing, I mean not the estimate, but the idea of doing something. The standard thing is to use causal, sort of causal nature. So have a global time function, or maybe you do it locally, then just locally. So use a time function, let's call it t, and then what you want that if is that if you know f, which is going to be box u, you're trying to solve box u equals f. If f is supported in t greater than or equal to 0, want, I mean, 0 is whatever, want u to be similarly supported. And so the nice thing is if you work in such a situation, well, if my flow is such that, and so that would be in global hyperbolic setting, you can go back to T negative. So you start at some point in T positive, you take the backward back characteristics, you go back to T negative. In T negative, your U is supposed to be 0, so this term, you work in such a function space so that U is identically 0. This is automatically 0. This is, of course, like you have a priori control, and this is a relatively compact error term. So that gives you a Fredholm version of the the estimates for Fredholm theory. So, okay, but this doesn't always work. So you want the estimate both for the operator and the adjoint, by the way. So technically, if you want to run this for the wave equation, you're really running it in a finite time interval, because in order to go forward, you have to be able to get to where the solution was 0 beforehand. And for the adjoint, it really means running backward in time. So in the future, somewhere the solution, well, for the adjoint thing, things are supposed to be 0. Okay, so that's one thing you can do. The other things that one can do, which I may or may not say, some of them may or may not say things much about. So one is complex absorption, which is very good for a number of things. But in this context, concretely, it's very nice for the spectral theory purposes. Like a version of it. So I will maybe mention something like this. So this means that the principal symbol already has an imaginary part. I mean, a non-trivial imaginary part. And so use that to control things. And two is exactly the things that correspond to what they ruled out here. So two is radio point estimates. So again, it won't work in the local theory for HG, but will work in many other settings. So you have to interpret things appropriately. And so what will happen is, so I'm going to call the operator P just so that make it clear. So it's not, if I want to work locally, it would not be the wave operator. For example, you might work in a say black hole setting, and you look at the trying to look at mode solutions. Then there will be a version of this happening. So anyway, these radio point estimates, what will happen is that, oh, I didn't say something that I wanted to say about this radio point business. So so I said that this HG could be just the dilation vector field. What that means in the quotient, in the cosphere bundle, is that the integral curves are single points. And so here, here what you would want to have is basically what you want to do is exactly the same sort of situation, or maybe a generalized version of this. But the upshot will be that so this radio points, so in S star M, one has a source or a sink, whichever way we're going, manifold. Actually, technically, including in the dilation direction. So technically, you are looking at sort of jet version, so infinitesimally at S star M, where you think of S star M as slightly differently. So you think it's the boundary of the fiber compactified cotangent bundle, which you might want to think of as a cobalt bundle. Okay, and so in such a situation, so the geometry now would look like this. I have my my cosphere bundle. Again, this really is the boundary of the cobalt bundle. So the fiber, you compactify the fibers of the cotangent bundle into balls. And so what we have is maybe a submanifold like this. This is my radial set. Let's call it L. And then this would act as a source or sink normally to the submanifold. So these would be the HP flow. And so if here in this case, the source, so it should be a source also going into the interior. And so what happens in this setting is, let's give this a name. This was my elliptic estimate. This was the, let's call it real principle. So in RP, one can drop the propagation term. So right, the structure of this is, if one thinks that the equation holds, then the structure is that if U is nice somewhere, then it's nice somewhere else. So you can drop the V2 term. If, there's an if, though, if this order S is sufficiently large, if S is bigger than some threshold value, which in, like, say, formally self-adjoint settings would be roughly like, so behaves like m minus 1 over 2, m the order of the operator. So there'll be some shift by sub-principal terms. So you can drop this. So this relates to what Dean talked about yesterday. So in a high enough regularity space, you can drop this, or if S is less than S0, then you have a version of RP. Still, when you're trying to propagating estimates from outside L to L. So say you have control. I'm trying to now go backward along the flow. I have control on these arrows somewhere over here, and I'm trying to get an estimate at L. Well, if I am able to propagate the estimates this way if I am in a low enough order space. So we put into a package, so a global package then. So in order to really have a global package, I just think of M as really a compact manifold. So then it's really going to be global. And what I need is a picture like this. So I will have a characteristic set. Actually, I'm just going to draw the characteristic set. So sigma sitting in S star M. And so if think of M as being two-dimensional, so the S star M is three-dimensional and the characteristic set is two-dimensional, so I can actually draw it, even by limited ability. So this is a torus. And I will have a source and the sink manifold, and the flow would be connecting these. Okay, so this is my sink. Maybe I want to do the other way. This is the source. And then what this is describing is that, okay, so here I didn't say anything about S because the general convention is I don't say anything, it's just a constant, right? And so here again, I didn't say anything. But like as Dean already alluded to yesterday, it actually will be very useful to have in this setting S to be a function. So this is the microlocal order of the Sobolev space as opposed to a constant. And then the point is that actually the elliptic estimates hold for any chord anyway. Right? I mean, the point is that nothing happens in the elliptic setting, so we'll hold. While RP holds, so here you have to be a bit careful whether you're going forward along or backward along the flow, propagating estimates forward. Along HG, if S is decreasing along the flow and switch sign backward. So I mean that sort of makes sense, right? So if you think of that box U is equal to 0, the constant S version says that if U was HS here, then U is HS here. So if I make S even weaker, surely that's fine. It sounds like, okay, I'm giving up too much. But no, because of course here I can allow box U to be in this corresponding space. So this is actually a sharp statement. You're not losing anything. So you should somehow think that for like Fredholm theory purposes, the single biggest thing is box U. So it's more important somehow than this. Okay. And so now the upshot is that so if S is chosen so that it's monotone the right way along HG flow, or let's call it P. So I have an operator P here. The operator on it, make it order M. Again, maybe, yeah, so there are various settings in which will this work. So monotone on the HP flow, and S is bigger than S0 at one of L plus L minus, and S is less than S0 at the other, then one gets global Fredholm estimates by just piecing all these things together. So it will look like M is the order. Okay, and same for the adjoint on dual spaces. So dual meaning that for the left-hand side, it should be dual of this. And that's the reason why, so one could say, oh, why don't I just have S large everywhere? That is the best of all worlds, right? The problem is that you have to have the estimates for the adjoint on the dual space. Okay, so that's the background why you have to care about the flow. And so based on this, the upshot is we want, for the non-elliptic problems we want to think about, ideally, in the best of all worlds, we'd like the HG flow to be well behaved, which what this means is somehow non-trapping, which says that, should say that all not-by characteristics tend to, well, some of these manifolds or submanifolds are in phase space or get nice estimates to, let me say, generalized, and not say exactly what I mean, sources sinks. Okay, so having gotten this far, oops, try to erase something. Maybe keep this. Okay, so what's the structure then? So we want spaces on which there's not geodesic flow, not barachastic flow, it has nice structures. And one space, so just to have a concrete example, would be spaces that look like Minkowski space and the various other signature versions of this. So you just take your favorite, whatever signature, translation invariant metric on your favorite vector space, finite dimension. And if you like excitement, you make it think about what happens. So an example would be, so G is, say, non-Riemannian. I'm just going to quote an Rn of whatever signature. And then what will happen is that, so what are the non-geodesics are just straight lines on Rn, and let's make it translation invariant for a moment. So non-geodesics are just straight lines. And sort of tending to null directions at infinity. So so infinity is very far away, and so one has the, seems, and so one feels one has a lot of ability to mesh things around. And in order to not mess things around, but concentrate on the goal, it's nice to think about a compactification of this. So this is really forcing us to face our problems, which is good. We should face our problems because eventually we have to anyway. So it's best not to try to postpone things. So let's face this. So compactify Rn to a ball like the fibers of the cotangent bundle. So here's the ball. Okay, so I have very limited drawing ability, so I'm going to draw the Minkowski signature. Okay, so even if I think it's 3 dimensions, I can't do better than Minkowski, right? So anyway, we will have this is going to be a 3-dimensional picture, which is beyond my usual ability. So this is the null, these are the null directions, and so the null geodesics go something like this. So this is the let's call them the tempered circles. So this is null directions. Okay, so that's what the null geodesics do. So it sort of looks like a sourcing behavior. And so in fact, you of course have to be in phase space. So if you look at T star Rn, so this is Rn cross Rn star really. So this is just the projection to Rn. And so what will happen is, okay, so one thing that I said was that I should always subtract the 0 section, which is, of course, honestly a statement when I think about local theory. So at infinity, things are a bit more exciting, and you shouldn't just forget about 0 sections. But forgetting about the 0 section for a moment, you would have exactly a sort of a, so in here, the HG flow has, so this sort of came up in slightly different terms. It has a source sink structure with sort of sources sinks at the conormal bundle in the appropriate sense of let's call this of S. So this would be the null. I'm just going to call it null infinity. So it's not quite scribe. Scribe would be like a blow up of this. This is my S. So that's the actual sort of phase space structure of the flow. And of course, one thing that happens is that the connectivity of the characteristic set as well as sigma, as well as S, depends on the signature. Of G. And so now this ties into what also has come up already, the work of Duister-Hermander. Which is that, so this is distinguished parametrices. So this this is in the local theory construction. So it this would not go directly anyway. So without significant further work, where you really think of infinity as honestly being there towards the Fredholm theory. But so from a local perspective, what they did, again, motivated by Whiteman and QFT considerations. So what they said was that if the characteristic set has k connected components, you get 2 to the k sort of distinguished parametrices, which is to say, what you do is that in each connected component, choose to propagate in one of two directions. Namely, you can choose to propagate your estimates along the Hamilton flow or against the Hamilton flow. Okay? That's a choice you have, and so you can make an independent decision for each of the components, and so you get 2 to the k choices. Now, in most cases, if you take this Minkowski, actually maybe just so that we're not stuck in actual translation invariant metrics, or so more generalized versions. So I'm not really going to say more about this, but e.g., work in a category like in a setting where if you differentiate, so let's just be in Rn. So if you differentiate the metric a bunch of times, then you should get, the more you differentiate, the more decay you get. So like a symbolic matrix. Constant. I don't know. I'm going to call my Euclidean variable z. And with some sort of asymptotic. So say, think of it as a classical symbol, and the asymptotic behavior should be, say, that of Minkowski or close to that of Minkowski. So close to a translation invariant one, say. But so not equal to necessarily, but just close to. Okay, so that's just so that nothing changes if you do this. So going back here, so for most signatures, so if you're not in low dimensions, that's when most really makes sense. I mean, you know, okay, 2 is bigger than 1, but you know they're pretty close, right? In the analysis standards are very close. So you have to be in high dimensions to be able to say something about most. So most signatures, we'll get that the sigma is connected. And so there are only 2 choices, so only 2 possibilities. Globally forward, or globally backwards. And so these are the these are the Feynman and anti-Feynman. But for Lorentzian, of course, there are 2 connected components, the Minkowski. And so, so correspondingly, you have 2 to the 2 is equal to 4 choices. The always forward, always backwards, and then plus the, you know, you switch your mind when you change characteristic sets, so they're the causal ones. Okay, so okay, so I didn't say anything about self-adjointness so far. So let me just say something about the. See, how much time do I have? Like 5 minutes or 10 minutes? Okay. So so the spectral theory side. So here you look at something like box minus lambda, and so okay, actually I wasn't specific about exactly what the spaces were for box. I just said this. didn't write down spaces. Dean actually mentioned, so for box itself, this would be B sub F spaces, so relative to the at infinity vector fields that are linear. This is in some sense more standard. So if I think here of lambda here, say positive to start, so I'm going to think of the actual wave equation here. So with and so these have an I in them. Okay, so this is my box, or whatever other perturbations. My box. In this case, the spaces would be, you can use standard weighted, Sobolev spaces. So that is to say, take your favorite Sobolev space on Rn and just put a standard polynomial weight. So things like H, S, L, which would be like Z to the minus S. It's just a Euclidean variable times HS, so decaying like order L. And then what this means, so the simplest way to translate this, okay, and I guess I won't talk about the strange Riemann example unless you ask me about this. So here the simplest way to get things going is that this L is what, so S is here going to be irrelevant, and this L needs to satisfy the flow inequality. So it's a variable. So it's a function, let's put this way, on the energy shelf at infinity, or just energy shelf period. It's non-Riemannian. So it's a function of the characteristic set. And so it would be like L bigger than and less than minus 1/2 in various places at sources sinks. And so again, lambda positive, I would still have this, and Minkowski's signature, I would have the 4 choices. If I have my sign of lambda right, as before. But now the spaces are slightly simpler. So let's just compare this. What happens if I change where lambda lies? So what happens is that if lambda, let's make lambda non-real. If lambda is non-real, then most of these possibilities disappear. So the point is that the imaginary part of lambda is the same order as box at infinity. So order 0 in the sense of decay. So the same order, and so this is the sort of skew adjoint part. So this acts really like acts as a complex absorption. And so basically what happens is that of all these possibilities, only choice that works. So you always have to propagate the estimate forward along the flow. So forward propagation, if I imagine them to be positive. But forward along the flow, if lambda positive, and backward and so that still gives you a Fredholm theory, and then say for the actual wave operator, it gives you inverses. So you get these things on this Feynman anti-Feynman spaces, so that the spaces corresponding to these things. Spaces, and moreover, the limits as m lambda go to 0 exist. So this is a limiting absorption principle. And the difference, if you take the difference, and I'm not looking up the sign, so I don't know what the sign is. So, but you have to take the correct inverse, right? So up, whatever. I don't know which one. One of these is positive. Okay. And so, so this actually also comes directly out of the estimates at the end of the day. So then a reasonable question is, this looks very much like a spectral measure. If I get my sign right, and spectral measure is supposed to be positive. So it turns out that in fact this is true. So in fact, box is self-adjoint, essentially self-adjoint. And so this is just the positivity of the spectral measure. So there's various works on this. So I started thinking about this because of a question by Dzerzhinsky, and Dzerzhinsky, Simpson, Nakamura, Taira, and others worked on this. Should also say that in this Minkowski setting, without the lambda, so it's earlier, it's work with Gell-Redman and Haber that sort of started this. And then the sort of QFT side of things was coming with discussions with Michal. And then maybe just one more thing, so there are refined versions, which sort of, I'm going to put like this blow up corner. So give better estimates. So this L restrictions are wherever they are a bit artificial, and so this is ongoing work with Viet, Dang, and Wrochna. And so the reason why I'm saying this is because this is relevant for something that they did. So this would be in the, say, Dirac setting, but it's relevant to what they did in the scalar setting, which is where they use the functional calculus to do Shamsuddin Cohn's spectral action principle. So to look at functions of box restrict to the diagonal, complex powers restrict to the diagonal, and look at the pose of the metamorphic continuation. So that sort of all sort of fits into this general framework. Thank you very much for your attention.